If you've heard of topology, you've seen this imagery. It's everywhere, from pop sci articles to classrooms to even dissertations, and it sucks. The idea is that topology describes shapes in their holes, and that mugs and donuts have the same number of holes, so are the same shape in some weird way. This is such an oversimplification that it completely misses most of topology. It's like acting like morality is just littering, and Logan Paul didn't litter, so Logan Paul is moral. It's deeply unserious, and misses the other, far more important parts of morality, like not scamming your audience. The same is true for acting like topology just describes shapes. Sure, it's part of topology, but acting like it is topology is genuinely damaging people's understanding of the field. Back in reality, topology is one of the most important fields for computational mathematics. Like morality, we were using topology well before we even knew what it was. It's so foundational that every engineer, physicist, and animator uses it without even knowing it. It's basically the thing you duct tape to algebra to get calculus, and you accidentally use it every time you say touch. So what is it? What is topology? Like describing morality, it's complicated, and not everyone agrees. I may think morality is about not causing harm, about not being bad. My friend may think morality is about following God's will, about being good. He defines good, I define bad, but either defines a morality. Topology is similar, except instead of good and bad, two things, it's five things. I'll introduce them one by one and rank how moral they are. First is the boundary, which is the edge of the set. They sit on the fence hard, can't decide if they're in or out, to the point where it almost seems intentional. It's hard to have an opinion on them since they don't have opinions of their own, so C tier. Next is the interior, and they're that clique of popular girls you see in movies. They'll drop you from the group for any reason, and then just bully you for the fun of it. If anyone outside the group even touches you, you're out of the group. They're just awful people, easily F tier. A breath of fresh air from the interior, we have closed sets, and these dudes are homies. They contain everything they touch, so they're as inclusive as you can get. It's hard not to be friends with them, so everyone in the boundary is in, but they didn't really do anything for that friendship, it just started that way, so only A tier. Next up is the closure, and every good thing you could say about closed sets, you can say about the closure, and more. They're inclusive enough to contain everything they touch, but they actually went out and did it. It's not like closed sets where it just started that way. They're the best, easily S tier. Finally, we have the open sets, and I hate to say it, but this is a straight up cult. Anyone the outside even touches is staying out. Everyone in the boundary is out, but they didn't really get pushed out, they just sort of know open sets are full of it. The only saving grace is that they actually believe what they're peddling, so it's not malicious, so only D tier. With this cast of characters, we can see what topology is all about. It just defines touching, when a set touches a point. Like good and bad, if I define any of these structures, I define the rest. Also, like good and bad, I can have multiple definitions of topology on one space. Then we get to what makes a valid topology. My baby brother may say that his morality is ice cream, but that doesn't make it true. It's not just that it's a dumb morality, it's just not a morality. It doesn't provide a framework to navigate individual interests in a society. If he said, everyone should make me ice cream, that's a morality, but a pretty awful one. Anyways, what makes a topology valid? We could look at any one of the five structures to answer that, but one's an S tier for a reason. Let's look at what makes a closure. The closure takes a set and adds all the points that are touching it. For that to work, it must meet four conditions. First, nothing touches nothing. More precisely, the closure of the empty set is empty. Second, the closure only adds points, so any set is a subset of its closure. Third, points are small. If a set touches a point, it's not big enough to go touch something else. It's a point, not a bridge. Rigorously, the closure does nothing to closures. Fourth and finally, a pair of sets is touching a point exactly when one of the sets is touching it. In set theory, the closure of a union is the union of the closures. These four criteria are called the Kuratowski closure axioms, and if a function fulfills them, it's a closure. And once you have a closure, you've defined touching. You've defined a topology. This doesn't seem like a big deal, but it's huge. It can be used to define countless other ideas. Not only can we define the boundary, the interior, open sets, closed sets, but so much more. Let's return to the mug donut to see one of them. Tearing. You can transform from a mug to a donut and back without tearing. Everything that was touching is still touching. Tearing is prevented and touching is preserved. You cannot do the same with a sphere and a donut. To make the donuts whole, we have to tear it open. We have sets that were touching but aren't anymore. We hate tearing for reasons that we'll get into later. We hate it so much that we even named functions where tearing doesn't occur. We call them continuous functions. But how would we define continuous functions? Well, we know the outputs must touch if the inputs touch. If they don't, tearing occurred. We know the closure adds the points that are touching, so a function is continuous if every point in the input's closure is in the output's closure. More concisely, if the image of the closure is a subset of the closure of the image. You may have heard continuity differently, something like you can draw it without picking up your pencil. This is because there aren't jumps, or discontinuities, or tears. They're all the same idea. To see this, let's consider the simplest discontinuity, the step function, which stays at 0 until you hit 0, then jumps to 1. In the input on the x-axis, the negative numbers are touching 0. After the function is applied, all the negative numbers go to 0, and 0 goes to 1. 0 doesn't touch 1, so the negatives aren't touching 0 anymore. 0 was torn from them. Now's a good time to take a step back and see how far we've come. First, we learned that topology is about touching, and that there's 5 different ways to define it. We chose one of these structures, the closure, and learned its minimum requirements, the Kuratowski closure axioms. We used the closures to define tearing, which we used to define continuity, one of the most important concepts in mathematics. If you're still watching, you want to understand math. You want to know what it's really describing and why we care. Luckily for you, that's literally the point of my channel, so like and subscribe and I'll keep making videos like this one. Anyways, returning to topology, we've left one major question unanswered. Why do I care? Why do I want to define touching? Why do I want to prevent tearing? Well, dear viewer, it's because you couldn't watch this video without it. Your computer has finite memory, and the world doesn't really care. You need some way to reduce how much data things take up. You need to approximate. But what is approximation? Let's think of trying to approximate pi with decimals. Since pi is irrational, we can never be exact. However, we can be as accurate as we want. We could get pi to 5 decimal places, or 50, or 500, but we can never get them all. As we build ever more complicated spaces, from the reals to the complex numbers to vectors, functions, vector fields, distributions, and more, we need a rigorous definition of approximation. We want our approximations to be accurate, so that starts with a rigorous description of accuracy. So, what makes an accuracy? Well, accuracies are the set of points that are considered close enough. More importantly, accuracies allow a little bit of error in any direction. You need to be able to walk around a bit without hitting the outside. It's like a little cult. The open sets would love these guys. In fact, they love each other so much that they did a fusion dance, and now they're the same thing. Open sets are accuracies, accuracies are open sets, and the outside refuses to touch either. This is the core duality of topology. Like how morality describes good and bad, topology describes touching and approximation. But this just shifts our original question. We want to describe accuracies, and we just learned they are open sets. But I still don't know what an open set is, so what is it? Exactly like the closure, open sets are rigorously defined with axioms. The first one is that the full space must be open. Since there's nothing outside the full space, the outside can't touch it, which is the defining trait of open sets. The other 2 axioms are about how you're allowed to combine open sets, or accuracies. They're a bit confusing, but I'll describe them with an analogy. Imagine your boss comes in with an infinite stack of papers, and each paper has an accuracy, an open set. The first paper may require the first decimal place, and the second paper may require the second. You're tweaking. I mean, there's infinite papers. What do they want you to do? Then they ask, can you find an approximation within one of these accuracies? Only one? That's so easy. You pick up the first paper, give them an approximation to within 1 decimal place, and they walk away happy. From this example, we can see that any, even infinite combination of accuracies is still an accuracy if you only need to fulfill one of them. In set theory, we say that arbitrary unions of open sets are open, our second axiom. For the third axiom, imagine your boss wants you to find an approximation to within every accuracy in the infinite stack. No shot. They're saying they want every decimal place? That's not an approximation. That's exact. You tell your boss it's impossible, and the boss says, fine, can you do it within the first 20 accuracies? Now that's doable. You can do any finite number of accuracies, but you can't do infinite. In set theory, we say that finite intersections of open sets are open, our final axiom for open sets. If we find a collection of sets containing the full set that you can take arbitrary unions of and that you can take finite intersections of, you have a collection of open sets. And once you have this collection, you've defined accuracies and you've defined a topology. In fact, this is what I mean when I say a topology. The collection of accuracies in the space is the topology of the space. Open sets are by far the most common way of defining a topology, and it's not hard to see why. We aren't defining touch for fun. When we apply topology, we are doing approximation. And when we do approximation, we tend to have some idea on what accurate should mean. So we start by defining the accuracies, the collection of open sets, the topology. But this leaves a few major questions, like how do closures fit in? If we define topologies using open sets and we're doing approximations, why do we care about closures? Well, the closure adds everything the set touches. And if a set touches something, how far away is it? Not far at all, as close as you could want. In other words, within any accuracy. The closure adds all the points that you could approximate to any accuracy. A point is in the closure of a set precisely when every open set containing that point also contains an approximation from the original set. This is the flip side of the closure. The closure's nightlife is all about touching, but its day job is all about approximating. We can start to use this to truly understand the closure, even in more complicated settings. We know we can approximate pi to any accuracy with decimals, so pi must be in the closure of the decimals. In fact, every real number can be approximated by the decimals. The closure of the decimals is the real numbers. This is why we can use the decimals for everything. It's because its closure is everything. It's a huge deal to have a subset of a space whose closure is that space. So important that we named them. We called them dense subsets. It means that we can approximate any point to any accuracy, and we really care about dense subsets. If we're approximating something on a computer, we're using a dense subset. Computers use binary to approximate the real numbers, so binary is dense within the reals. Computers use polynomials to approximate continuous functions, so polynomials are dense within the continuous functions. Computers approximate vector fields like the ones used in fluid simulations or weather modeling. They store a finite sample of vectors that approximate any other vector in the field. Those samples are dense within the space of vector fields. As we build ever more complicated spaces, we need some way to approximate them and compute with them. In other words, we need a dense subset on the computer. Remember, everything on a computer is represented by binary, which are zeros and ones. Each of these binary numbers represent a whole number, so you need a dense subset that can be represented by whole numbers. We call this a countable dense subset. Countable is one of the worst names in math, because infinite sets can be countable. You can't count them all, but we call them countable anyways. I think it should be called listable because you're putting them in a numbered list, but what do I know? Anyways, if you find a countable dense subset, you can approximate anything to any accuracy on a computer. In other words, your space is computable. This is an unbelievably important idea for doing anything on a computer. Like, your space needs to be computable to even pretend like you're going to do anything on a computer. Unluckily for us, spaces with countable dense subsets were named before computers even existed. And the name they chose for it, probably the worst name in all of math, was separable. If you can approximate anything to any accuracy on a computer, your space is separable. I will never, ever use this wording. Like, what are we even separating? We are literally doing the math that defines touching. Separate means not touching each other. The word has a full-time job and we're just going to force it to work a part-timer. No shot. A space where you can approximate anything to any accuracy on a computer is computable, not separable. Anyways, we're starting to piece together why topology is so interesting and why we need it. It's the rigorous backbone for both touching and approximation, and you can look at everything in topology from either perspective. An example of this is dense subsets, which were actually named thinking about touching. If you're thinking about physics, the name seems kind of random. Like, does bro have more mass or less volume? Think about a dense jungle instead. Anywhere you stand near a dense jungle, a plant is touching you. Anywhere you stand near a dense subset, a point is touching you. To complete our journey, I told you that we hate tearing, but I never told you why. To see why, let's look back at continuity with our new perspective. We saw that it preserves touching with the closure, and now we know the closure also describes approximation. From this, we see continuity preserves approximation. Every approximation in the input of a continuous function makes a valid approximation for the output. You may have seen this with continuity-preserving limits, which are a type of approximation. We can see an example of where this fails with the step function. 0 until 1, then 1 from then on. In the input, we can approximate 1 with 0.9, then 0.99, then 0.999. We can keep adding 9s forever until we get as close as we want to 1, approximating 1 as accurately as we want. However, the step function maps all of those approximations to 0. Our input gets as close as we want to 1, but our outputs are always 0. They never approximate 1. We can approximate the input to any accuracy we want, but we can't use it to approximate the output. The function fails to preserve this approximation, so it's discontinuous. It has a tear. And this is why we hate tears so much. Every tear is an approximation that doesn't work. This is why engineers and physicists and animators care about continuity, and topology to be honest. If you're using a function on a computer, you need it to be accurate. You need it to be continuous. Otherwise, your code could just spit out something wildly wrong or divide by 0 and fail in some other way. If the function is continuous, it doesn't tear. It preserves approximations, and you never get these failures. This idea of preserving approximations gives us a whole new way to define continuity. Earlier, we defined continuity with closures, which is great for seeing how continuity preserves touching. It's pretty damn useless for approximation though. What we really want is a way to give it some desired accuracy, then for it to give us the accuracy we need. We want to pull back any output accuracy to some input accuracy. We say this rigorously by saying every open set has an open preimage. This is the most useful definition of continuity for approximation. It's basically a machine that does exactly what we want continuity to do. Take my desired accuracy, then give me the accuracy I need for my approximation. An example of using continuity like this is approximating the square root of pi with decimals. It's impossible to get exact, so you get as close as you want instead. You choose your desired accuracy, use continuity to get the necessary input accuracy, choose a decimal approximation that's within that accuracy, then square root that approximation of pi. You'll need to approximate the square root with decimals, but you know you can because the decimals are dense. It's complicated, but it shows why we need density, continuity, and the rest of topology. Imagine if this was a climate model, or a stock portfolio, or a simulation of the Big Bang. Sure, simulations are way more complicated than the square root of pi, but the structure's still the same. Approximate with a countable dense subset, apply something continuous, and get an approximation back. This is how we landed on the moon, animated Pixar movies, and trained ChatGPT. Never going for an exact answer, but aiming for approximations that were close enough. And at this point, we've covered everything I have time for. I hope you leave feeling like you understand why we need topology. It's core to nearly every field in higher math, from computation to analyzing shapes. I mean, integrals and derivatives are literally defined with limits, which are a type of approximation, so they need topology. Calculus needs topology. If you like understanding rigorous definitions, I have another video on my channel about the 5 structures that define topology. It covers the main properties of those structures and how to define them all from any starting point. Regardless, like and subscribe, and I'll see you next time. Bye-bye.